Great pleasure to introduce Professor Oriol Arteaga. He completed his PhD from University de Barcelona in 2010. He joined the BATCA group at New York University from 2011 to 2013 as a postdoctoral fellow. Currently, he is an assistant professor in the Department of Applied Physics at University de Barcelona. His research interests broadly lie in experimental and theoretical aspects of light-matter interaction related to the polarization of light. Today, he will be talking on phase and polarization from Fresnel-Arago interference law to Pancharatnam geometrical phase. Hopefully, next time we will be able to invite you to our campus. I request the audience to reserve the question for the discussion section unless it is important. With this, over to you, Professor Arteaga.
Thank you very much for this introduction. It's a pleasure to present this work in this student chapter. I hope you will find it interesting. So yes, the title, it's as you can see, is from Fresnel-Arago interference laws to Pancharatnam's geometric phase, and it's a mixture between teaching, research, and history talk. So it's a mixture between all three things. Let me start with some short information about where I am or where I am placed. So I work in Barcelona, which is a city here, which is the capital of a part of Spain that is called Catalonia here. So Catalonia is this northeast part of Spain, and it's a very touristic city. You can see how it looks like from the mountain that is close to the city. So the city is touching the Mediterranean Sea, and this is the most famous building there. Probably it's Sagrada Familia. You have heard about it. So I work in the University of Barcelona, which is the oldest university in Catalonia, and this is the historical building of the university, and this is the actual building where I work. This is the physics faculty in Barcelona, which is downtown in Barcelona, but not in the center as the historical building, but a little bit in the north part of the city. So I work there, and I work doing basically polarimetry. So my main research topic is, I can say, it's Muller matrix polarimetry. This is a quite general topic. So in fact, I specialize more in these research lines, particularly in ellipsometry. That is a technique focused on the determination of the optical constants of materials on the electric tensor mostly. Also, during my PhD and later during my postdocs, also I worked a lot in doing optical activity measurements, so trying to quantify the chiroptical properties in crystals, in organic compounds, also in some metamaterials. A third aspect I usually work is building instruments. So I like to spend time like putting together polarizers, compensators, and building instruments. For example, this is an ellipsometer that we recently built in the lab with some Fresnel ROMs and some polarizers. So and in this configuration, that is the typical configuration for ellipsometry. I also work in more theoretical aspect related to the interpretation of measurements, on phenomenological interpretation of Muller matrices mostly, and also something that I personally like to investigate or to read about is the history of polarimetry and the history of polarization of light. And in fact, this talk that I will present today is quite related to this last point, the history, but also contains some research aspects. So let me move to the contents of my talk. Well, I have to say that all this, the point of unification is the polarization of light. This is the main point. So what I am going to talk about today. So I will start with a very short introduction about the concepts of polarization and phases. So you probably you know everything about this first point. Then I will move to something that is not always in all books, that are the Fresnel-Arago interference laws, and I think are quite interesting. Then I will introduce the work of Pancharatnam. This Indian researcher made very important contributions to the theory of interference of polarized light. Then I will continue with some history about the geometric phase and the polarization of light related to the, geometric phase and polarization of light are two things that are super related, so it's impossible to split them in two. And in the last point, I will move on more research aspects and new materials and metamaterials that use the geometric phase to make fancy new optical effects. So some basic ideas about polarizations and phases. Basically, here we will describe the plane wave. The plane wave that is a solution of Maxwell equations. So basically, we have here our electric fields here. And if the wave is propagating along the z direction, we basically only need two components of the field. Basically, we need to take care of the x component and the y component. So usually, this is the full description of the electric field. But to describe polarization, we don't need everything that this equation is showing. In fact, to describe polarization, as you have here, it's enough with 3 parameters. So basically, we need the amplitude of the electric field along the x component, the amplitude of the electric field in the y component, and the relative phase between the two components. All the other things we can, you see, all these other terms can be grouped together in something that we can call the overall, the global or overall phase of the wave. That it will quickly be oscillating because it will depend on the temporal point and on the spatial point. So we, in general, in polarimetry, we are not going to keep track of this global overall phase. We will only worry about the polarization parameters. So we will worry about these parameters. As we have a vector with 3 components, but the last component is 0, we can simplify this 3-component vector into a 2-component vector. That is what is called a Jones vector. The Jones vector is a complex vector of 2 components. Again, as we only need 3 parameters to describe polarization, in fact, this Jones vector also contains one additional parameter, that is the phase. That in most experiments, in most polarimetric experiments, will play no role, but it will be essential for interference experiments. So here we have our 3 parameters that describe polarization. Okay, so we have this Jones vector. If we want to transform this Jones vector, we use a Jones matrix, which is a 2x2 complex matrix that transforms these Jones vectors. For this presentation, it will be quite important to refer to the Jones matrix of a linear retarder. Okay, so let's put that as an example. A linear retarder is an optical element that introduces different retardants for 2 perpendicular polarizations. So the Jones matrix of a linear retarder introduces a retardance that is shown here as delta x for the x component, and a different retarder and a different retardance delta y for the y component. Okay, usually these retardants are related to the different speeds of propagation of light in this material. This kind of material is called a material that is birefringent. Okay, that has different speeds of propagation. So here we can write the Jones matrix of a linear retarder as it is shown here. But this we can normalize, for example, this Jones matrix, and we can write it also in this format here that you have here. So that it depends, the matrix itself, it depends only on the difference of speeds of propagation of the two components of light. And the other term that goes outside, it's a phase term. Okay, it's a phase term that is related to the speed of propagation of light in the material, in the material. Most usually, instead of writing the Jones matrix of a linear retarder like this, we write it as it is shown here. Okay, it's fully equivalent. It's fully equivalent, but the difference is that we can call that this phase is like an isotropic phase, because it's the average of the speeds of propagation in the material. Okay, it's not depending on the anisotropy of the material, and this part that depends only on delta is the polarization transformation. So in general, when light propagates in a linear retarder, there is a modification in the polarization of light, and also there is a modification in the phase of light. Okay, so this modification in the phase, it's unavoidable. It's always there, even if the material is not anisotropic. For any material that have a certain refractive index, when the light propagates through it, it gets a change in phase. But in general, as I have said, polarimetry disregards phases and keeps only polarizations. So in general, when we refer to Jones matrices, usually we neglect this part here and we keep only the polarization transformation, usually. Later, we will come back to this thing. Another important point are the Stokes vectors. You probably you know about them, so it's not necessary to define them. Basically, the only important point to remark is that we can measure them. They can be defined in terms of intensity, so are directly things that we can measure. We cannot measure the electric fields, but we can measure the intensity. So it's something that we can measure. And for this work, for this presentation, it will be especially important, this representation on the Poincaré sphere. Okay, I'm sure you are very familiar with this, so it's not necessary to go through it. It's only to remind that all completely polarized states are in the surface of the sphere, and the states that are partially polarized are inside the sphere. The Stokes vectors can be also defined in spherical coordinates based on angles and azimuths in the Poincaré sphere. But if there is no depolarization, in fact, the Stokes parameters fulfill this condition here. So if there is no depolarization, we can all, it's enough to use three Stokes parameters. As we have said, fully polarized light is described only by three parameters. The Stokes vector, as we have said, was defined only with three parameters. Only when we add the possibility of having partially polarized light, we need to consider an extra parameter. And then this condition will not be fulfilled. Okay. Another word about Muller matrices. I'm sure you are also familiar with Muller matrices. Basically, are 4x4 real matrices that transform Stokes vectors. Okay. The nice thing is that we can measure them. So many of the instruments that are available in labs working with polarimetry applications nowadays measure Muller matrix terms. And Muller matrices can be used for any description of a scattering experiment. By scattering, I mean specular reflection, I mean non-specular reflection, transmission, diffuse scattering, whatever kind of interaction, we can measure the associated Muller matrix. And another important point is that the Muller matrix contains no phase information. So the Muller matrix do not keep track of these phases that you see here. So this, when we move to the Stokes-Muller formalism, all these phases vanish, okay? So we don't need to worry about phases when working with the Stokes-Muller formalism. So, but as we want to keep track of phases, because in this presentation I am discussing the geometric phase. For most part of this presentation, I will use the Jones formalism. Okay. Sometimes I will also use the Muller formalism, but most of the time I will be using the Jones formalism. Okay, this is the end of the introduction. So let's move to one of the main topics of this talk, that are the Fresnel-Arago laws of interference. So this is a quite interesting aspect, because it was published very, very long ago. So all this goes back to this publication from 1819. So more than 200 years ago. And it was quite incredible that Fresnel and Arago published this work. And this is an experimental work. So it's a work that it's a long work, many pages, describing experiments, basically. And at the end of this work, they write as a conclusion 5 laws of interference. You can see them here. So this is the first one, this is the second one, the third, the fourth, and the fifth law. At the moment, we will focus about the four initial laws. So only the first, the second, the third, and the fourth. We will omit the fifth. That is what usually you can find in books. If you research in books or in Wikipedia about the Fresnel-Arago interference laws, you will only find 4 laws, not 5. Later, we will discuss about the fifth law, okay? So this is in French. If we translate these laws to English, we find these 4 famous laws. So the first one is basically saying that light waves with orthogonal polarizations cannot interfere. The second law is saying that polarized light waves with the same polarization can interfere. The third law is a little bit more subtle, and it's saying that if we have 2 laws with orthogonal polarization coming from a natural, from for example, from the sunlight, for example, and we bring them together to a common polarization. For example, we add a third polarizer to make the polarization coincide. They will not interfere if they were initially unpolarized. The fourth law is similar to the third, but it's now saying that if the original wave was already polarized, then when these 2 orthogonal polarizations are bring together to a common polarization, now yes, they will interfere. So third and fourth laws are a little bit more subtle to understand. So we will discuss them more in detail now with an illustration, okay? We will illustrate basically the third and the fourth laws. And to illustrate them, we will use a very famous phenomena that is happening in many crystals. Basically, it's happening in almost all birefringent crystals. That is double refraction. I'm sure you are familiar. It's based on the existence of birefringence in a material. And the most famous effect is found in calcite because it has a very high birefringence. And the type of calcite that has a highest purity and it's very transparent, it was coming from Iceland, and it's why it is called Iceland spar, because this is a type of calcite with very high purity. And it was giving very nice double refraction. Double refraction basically consists on the splitting of light into orthogonal components with two perpendicular polarizations. For example, if we have a incoming light that is linearly polarized at 45 degrees, and we have a piece of calcite, okay? If we orient properly the piece of calcite, okay, as it is shown in this picture here, we can split this 45 degrees polarization in two different rays. One with horizontal polarization and the other with vertical polarization. And both of them will have the same intensity if the initial ray was polarized at 45. Okay, this effect was known by Arago and by Fresnel. So basically, all their experiments were based on double refraction effects because it was the easiest and the best way they had to polarize light and to split light and to split waves into orthogonal components. So let's go back to the laws and try to see what happens when these laws are applied to double refraction. So in this experiment, we consider a light source, in principle, incoherent light source. Like I have put here, for example, a halogen lamp or a LED light. We put a lens so that we make the light to converge, slightly converge into the calcite crystal, focus here in one of in the crystal itself, and then diverge. So what happens if we do that in calcite? So as basically the crystal will split, incoming light will be unpolarized. Incoming light here will be unpolarized, but it's possible to split unpolarized light into horizontal and vertical components. Okay, so light will be no longer unpolarized, but it will be polarized after going through the crystal. But here there will be no interference, okay? Because the first Fresnel-Arago law is telling us that orthogonally polarized light cannot interfere, okay? Now let's consider what happens if we add a polarizer at the outset. Here we add a polarizer. So these two polarizations, the horizontal and the vertical polarizations, will be brought together to a common polarization, to 45 degrees again. So now, are we going to have interference here? So there will be interference fringes here or not? The answer is that in this case, we are not going to have interference because the original source here, this source, was unpolarized. So the light reaching the crystal was unpolarized. And the third Fresnel-Arago law is telling us that there will be no interference fringes in this case. The situation is different if we add a polarizer here, okay, before entering into the crystal. So here, light that is reaching the crystal is already polarized, okay? Then it's split again into components. Then it is polarized again. And as it has the same polarization, so it can interfere. And in this case, it will interfere because now we are under the conditions of the fourth law. Okay, so this is the subtlety that makes the difference between the third and the fourth law. Okay, otherwise they are similar. So the key point is if the initial light was polarized or unpolarized. Okay, this is the illustration, the experimental illustration of the Fresnel-Arago interference laws. Another remark about the experiments they did is that this experiment, the experiment on calcite, this double refraction experiment, is in fact analog if to the double slit experiment, to the famous Young experiment. If we put orthogonal polarizers in the slits, okay? If we put a polarizer here in this slit and another polarizer here in this slit, and we check for interference fringes, we get basically the same type of answer that we were discussing now for the experiment in the double refracting crystal. And I am making this analogy because this analogy was in fact done by Fresnel and Arago. So if you read the original manuscript, sometimes they discuss the Young experiment, and sometimes they discuss the double the double refraction. Okay, so it's an interesting thing to know that this is, at least from a qualitative point of view, this is analog. Okay, so we are more or less in this point of history. Okay, what we have been discussing happened in 1819. So at that time, only like 10 or 11 years had passed since Malus had discovered the polarization of light by reflection. So polarization was really new at that time. Although the effect of double refraction was known since long ago, okay, but it was not really attributed to polarization. So the concept of polarization was really new. And in fact, at that time, only linearly polarization was well known. Okay, it was a little bit later in 1822 when other forms of polarization, like elliptical polarization and circular polarization, were described. Okay, but at that time, only linearly polarized was well known. But still, what they achieved was very remarkable. These laws were very remarkable. The next point in our historical review is the work of Pancharatnam. Okay, that was in the 20th century already, and is what we are going to discuss now. This work, okay, this the theory of interference that he developed. So before starting to discuss his theory, only a small remark. I mean, she was, I think, in Bangalore working. I'm not sure I'm pronouncing it correctly. And well, I mean, in fact, he was not for all his career working in India. In fact, only the initial years. But the unfortunate thing is that he died when he was very young. He died with only 35 years. And in fact, many of his most important, of more famous publications were made when we was only 20 20-something. He was really, really young. And in fact, there is this website that is collecting all the publications of Pancharatnam when he was in India. So we will the work that we will discuss in this presentation is based on these papers. Particularly, I think in this paper that is number 7 here. So basically, we will discuss this paper over here. Okay. After some time, he moved to United Kingdom, and I think he got sick, and he did not he could not survive for very long after he moved back to after he went to Britain. Okay, so we are going to discuss this paper, which is a difficult paper, I have to say. It's long paper and contains many experimental aspects and also many theoretical aspects. So it's very interesting, but difficult, I have to say. It's not easy to follow Pancharatnam's papers, but it's interesting. The most important point is that he's trying to work to deal with problems in crystal optics. In fact, he's looking to something similar to double refraction, but not strictly double refraction, because in double refraction, we have a linearly polarized light that is split into orthogonal components. Pancharatnam was studying more complicated crystals. In fact, he was studying crystals of low symmetry that were biaxial and absorbing. In these crystals, when you shine light into the crystals, you get a phenomena that is similar to double refraction, but it's different in the sense that the two states that you get are not orthogonal, okay, are not fully orthogonal. As they are not orthogonal, some interference can be seen sometimes. So he was trying to understand the interference he was seeing in these biaxial crystals. Okay, and he was trying to understand this. So it's still remarkable that both Fresnel and Arago and Pancharatnam were working in things that were not so different. Okay, they were still crystals. So Pancharatnam made two essential findings. The first one, he provided an answer to this question. So how does one define a phase difference between two light waves which have different polarization states? Okay, so which is the phase difference between two states that do not have the same polarization? So the answer he gave, it's right in here, it's this part highlighted here, is that the phase difference is the change that we have to apply to one of them. So we have to apply a phase change to one of them in order to maximize the intensity of their superposition. So it means that we want to make maximum the intensity of their interference. Okay. So expressed in mathematical terms, it turns out that a Pancharatnam result can be expressed as a complex scalar product. Okay, so if we have two states that do not have the same polarization, let's call them A and B, and we want to know which is the phase difference between A and B, we can compute what is called the complex scalar product between them. Okay, and calculate the argument of this product, and this argument will be the phase. This thing this result is sometimes called Pancharatnam connection. So because it is a connection between two states that are not in the same point of the Poincare sphere, that are separated by a distance, and we can say if these 2 points are in phase or not in phase. For example, let's consider these two Jones vectors, A and B. They are different, so they have different polarization. Obviously, they have different polarization. We compute the complex scalar product. Okay, we transpose this one, we take the complex conjugate of it, and we multiply by the second, and we get an answer. Okay, this answer, if we calculate the argument of this, this is a complex number. The argument is different from 0. So this is basically telling that they are not in phase. These two states are not in phase. Let's consider a second example. Okay, these two different states. The polarization is different, but now if we repeat the complex scalar product between them, we get a real number. If we calculate the argument of this number, the argument, as this is a real number, it will be 0. So there is the 0 is the phase difference between them. So they are in phase. These two states are in phase. So Pancharatnam gave an answer to this question. Okay, gave an answer to this question. The second thing he did was not exactly this, because you cannot find this statement in his paper, but something very related to this. In fact, Pancharatnam showed that if, for example, A was in phase with B, two different states, and B was in phase with C, not necessarily A was in phase with C. So there was no transitivity in between the connection. So A can be in phase with B, B could be in phase with C, and it could happen that C and A were not in phase. Okay. In fact, this statement can be made more general by this sentence that you have here, that is telling us that if a beam of light is taking along a closed circuit on the Poincare sphere, the beam is acquiring an extra phase that is equal to half the solid angle subtended by the closed circuit. So we move from A to B to C and back to A. We find that there is a phase difference between the initial state and the ending state if we keep doing these light transformations. And this phase difference was equal to this solid angle, this area of this triangle that I am indicating here. Okay, this is something quite interesting. Quite interesting because it's giving a geometrical explanation, a geometrical interpretation. In fact, this is related to geometry, as I have said. It's related to a concept that is called parallel transport. That if, for example, we have a vector here, a blue vector here, and we start from point 1 to point 3, and we transport this vector, this blue vector, in the surface of the sphere, following a geodesic, that is the shortest path between 2 points in a sphere. It's like a straight line, but in the surface of a sphere. If we do so, trying to keep always the same orientation of the vector, we find that, for example, we can transport 1 to the point 3. And 1 and 3 will be in phase if we do parallel transport. Okay, now we can transport 3 to 5. Okay, you can transport 3 to 5, and 3 and 5 will be in phase because we have done parallel transport. Now we can transport 5 to 7. We can go up, 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 and transport it here. And 5 will be in phase with 7. But if now we compare the initial point 1 with 7, we see that they are no longer in phase. 1 is not in phase with 5 and 7. And this is, well, this is exactly what Pancharatnam found. And it related to the this spherical geometry, okay? And it was demonstrated by him that this phase difference is related to the solid angle, okay, to this solid angle of the path. This seems complicated, but we will see some examples, okay? So this is, in modern terms, what Pancharatnam found. But the work of Pancharatnam did not had any impact at the time it was published. It was published in the 50s, but it was there. It got no citations, okay? Not even in India, I think, or almost no impact. So, okay, it stayed there. But then in the 80s, Michael Barriel published a famous paper in a different context for quantum mechanics, showing a geometrical phase, okay, showing a geometrical phase. And I think that Michael went to India at some point. And there in India, somebody pointed out that what he had discovered in that context of quantum mechanics was somehow related to something that one student years ago had done in India. And Michael wrote a paper where he explains really this history. So that when he was flying back from India, he was reading the original papers from Pancharatnam, and he realized that really what he was showing was equivalent to his work, but in the context of polarization of light, and it was really relevant. And it was at that time, after this publication, okay, that it was when the work of Pancharatnam gained all the recognition. Okay, it was not until the late 80s that really Pancharatnam's work was really known. And this is probably the reason why in optics the geometric phase is sometimes called Pancharatnam-Barriel phase. So if you search for PV phase in optics, you will find a lot of applications, a lot of papers referring to this phase. Okay, all this is sort of complicated, but let's see some examples. Because the good part is that we don't need to be good at geometry to understand geometric phase. Because the Jones calculus keeps track of that. In fact, the Poincaré sphere, it's a nice geometrical interpretation, but we don't need to use it if we don't want, because it's enough with the Jones calculus. So let's, for example, consider the following transformation. We have a linear polarization. We use a quarter wave plate oriented at 45 degrees with respect to the azimuth of this polarization. We convert it to circular polarization, and we use a linear polarizer to convert it to linear polarization again. So we start with linear and we end with linear. But in meantime, we do some transformations. Let's see this transformation. So to do this, basically we have to compute what are the Jones matrices of a quarter wave plate at 45 degrees. Okay, we write the Jones matrix of a quarter wave plate. We rotate by the angle 45 degrees. we get this answer. For the linear polarizer that is rotated to a certain angle, we take the Jones matrix of a linear polarizer of an horizontal linear polarizer, and we rotate to a certain angle, and we get this answer. Okay, now we have these two matrices. We can do the transformation. So we start with our horizontal polarization. We transform to circular polarization, and we go back to linear polarization. So we do this transformation. If we do this calculation, we get this answer. Okay. Interestingly, we see that something can be factored out. So something is factored when it multiplies both elements of the vector. Now let's consider almost the same transformation, but instead of orienting the quarter wave plate at 45, let's orient it at minus 45. Everything is the same. The only thing that changes is that here we had a minus I, and here we have I. Okay, if in the previous slide, instead of putting 45, we put minus 45, we have to change the value of this sign here, and then this minus will go away. And we get this answer, which is the same polarization. You can see it's the same polarization because the Stokes vector is the same, but the phase is different. Okay, they have a different phase. Okay, and this phase is different, but the optical elements are the same. So this difference in phase cannot be coming from differences in the thickness, for example, of the optical elements, because it's the same optical element, only that we have rotated a different angle, but it's the same element. So this is not coming from thickness changes, path differences. No, this phase that we have here is coming from polarization transformations. Okay, and this is the important point for a geometric phase. We can say this is a geometric phase. Okay, and the only thing we have done is we have done a simple Jones calculus, nothing else. If we want to do some geometrical interpretation, we can do it. Okay, so in the first transformation that I have calculated, we start with linear polarization, horizontal polarization here. We start from this point of the Poincare sphere. We move to right-handed circular polarization. We move from the equator to the North Pole. Okay. We then go back to the equator to a different linearly polarized state. Okay. If we do the same transformation, but instead of going to right-handed circular polarization, we go to left-handed circular polarization. Instead of going to the North Pole, we will go to the South Pole. So we'll go from the equator to the South Pole and then back to the same polarization state. If we consider both transformations, light here and here will be able to interfere because they will have the same polarization, but they are going to be out of phase. They will have, sorry, not out of phase, but they will have a different phase. And this different phase will be related to this solid angle, to the solid angle, okay, that is defining these polarization transformations. So the difference in phase will be, in fact, related to this orientation angle of the linear polarizer. Okay. So the solid angle that is enclosing this path is 4 times phi. As the geometric phase is 1/2 the solid angle, we have that the geometric phase is 2 phi. Okay, is this angle here. But we can do, instead of doing this geometric verification, we can do the verification using the Pancharatnam connection. We take the final state A, this state A here, the red state, and the blue state B. And we make the complex product, okay? And we do this product and check which is the argument of the result. The argument is 2 phi. And this argument is the difference in phase, is the geometric phase. Okay, so it is okay to use the Poincare sphere, but it's not mandatory to use. It's enough to use the Jones calculus and then verify the interference, the superposition using Pancharatnam's connection. Okay, I hope this example was somehow clarifying the calculation. If you want to read more about this, a more divulgative work, I recommend this paper, The Interference of Polarized Light. It's like kind of divulgative article, but very interesting. For example, I enjoyed this analogy that that the author makes between the geometric phase and the journey that that Phileas Fogg did when trying to making a travel around the world in 80 days. So they make the whole trip. They thought they were losing the bet because they had seen like more than they had already seen 80 sunsets. So they thought that 80 days had passed, but they didn't realize that when traveling around the world, they won 1 day by doing the round trip. So it's sort of related to the spherical geometry. So it's something interesting to think about. Okay, so this is the end of this part that is devoted to the work of Pancharatnam. But now I want to go back again, back to the work of Arago and Fresnel. So let's go again 200 years ago. Okay, we have the contributions of Pancharatnams, we have seen them, and the rediscovery from Barriel of the work of Pancharatnams. But we have something missing still. It's about the fifth law that Fresnel and Arago brought. Okay, this is in French. If we try to translate this law, we will find something not very clear, hard to understand. Okay, let's read it. In the phenomena of interference produced by rays that have undergone double refraction, the place of the fringes is not determined uniquely by the difference of path and the difference of speeds. In some circumstances, which we have indicated, it is necessary to take into account a difference equal to half wave. So he's saying that in some circumstances, sometimes it's necessary to take into account a half wave phase difference that was not that could not be justified by path differences. So this is something surprising. And in fact, when reading this, I was not able to understand what they were referring. So I had to really read the experiments they were doing. Okay, so this is what I tried to imagine the experiments that that Fresnel and Arago did. Okay? And this is what I am trying to explain to you. The context of this is that at that time in 1819, only linearly polarization states were well understood. They were not able to distinguish between elliptical and circularly polarization states and polarized light. So for them, like elliptical and circular polarization states were something not really different from unpolarized light. But linear polarization states were very clear to them. So they were considering an experiment similar to this one. Okay, don't be afraid of this. It's basically a succession of 3 different double refractions. So we have 3 different crystals, okay, double refracting crystals. In the first one, they basically separated unpolarized light into 2 orthogonal components, horizontal and vertical. Okay. The second crystal was placed at 45 degrees. So they were splitting the horizontal component into 2 components, one at 45 and the other at minus 45. The same for the second lay. And in the third crystal, they were doing again another splitting of the 45 degrees component, again in horizontal and vertical components. This is exactly what they were doing. Okay, not as simple as this, because they were the type of crystal was not the same in 3 cases, but essentially the idea is this. And they were comparing the interferences here at the outset. The interferences, obviously interferences between waves carrying the same polarization. For example, between this horizontal polarized wave and this one. There was interference or not? And they saw that in some cases, they saw interference fringes, but not the type of fringes that they expected, but fringes shifted 180 degrees with respect to what they expected. Let's see this. Basically, they compared the interferences between these 2 beams and these 2 beams. In the first case, they compared a wave that went from unpolarized to horizontal to 45, again horizontal. So unpolarized horizontal minus 45 horizontal. If we do the Jones calculus of this, so this is horizontal light, this is 45, this is horizontal again, we get horizontal. If we do from horizontal to minus 45 to horizontal, we get the same answer. Okay, this is let's call it the normal answer. Okay, this is the normal answer. They got interference fringes. But in this experiment, they were also saying interferences between waves that went from horizontal to 45 and then to vertical, and to horizontal to minus 45 and then to vertical. You can see that the only difference is that the last polarizer, instead of being horizontal, was vertical. And in this case, they saw that the interference pattern was shifted by 180 degrees, half wave. Okay. In modern days, we can say that this phase difference is coming from this minus sign here. Okay, this minus sign, but the effect of the interference is shifting 180 degrees, and that's why in the 5th law, Fresnel and Arago brought that in some circumstances that they have specified within the manuscript, they needed to consider this half-wave difference to explain the fringes they had observed. And this is a remarkable result, taking into account that it was more than 200 years ago. Because this is the earliest measurement of a geometric phase. And this is indeed a geometric phase. Why? Because, for example, we can make the representation in the Poincaré sphere. In the first case, in this case here, in the normal case, okay, the clip on the Poincaré sphere was from horizontal, in one case to 45, in the other case to minus 45, and then back to horizontal. Okay, the path is this green, sorry, this red line here. This path is not enclosing any solid angle of the sphere. But in the second case, they started at horizontal. One wave was going to minus 45, the other wave was going to 45, and then they were joining again, but in the vertical state. So the path here of the waves on the Poincaré sphere was enclosing 1/2 of the sphere. So the solid angle of this path is one hemisphere of the sphere. So if the full sphere is 4 pi, 1/2 is 2 pi. As the geometric phase is half the solid angle, so the geometric phase is pi. So this is the first geometric phase that was described in history, to my knowledge. And it's very relevant that it appeared as early as that time. And in fact, this was quite surprising for Fresnel, especially because Fresnel was very interested. And in fact, he made a different paper, in this case, a paper from 1821, where he was discussing a lot the results of this experiment. Okay, and we have to think that at that time, the Poincaré sphere was not invented, let's say it that way, but he gave a geometrical interpretation because he justified that there was no extra phase when the states were brought together by a contrary motion. So the states are brought together by a contrary motion, like we see here. This is a literal from Fresnel's work, even if the Poincaré sphere was not invented yet. So he gave a geometrical interpretation that is equivalent to consider the equator of the Poincaré sphere only. And on the other hand, the pencils whose planes of polarization are brought to coincidence by a continuance of the same motion, they reach a complementary image. They need this added phase. Okay, so a continuance of the same motion is exactly what we see in the Poincaré sphere. The first motion will be this one. The continuance of the same motion will be this one. So we are continuing the same trajectory. We are closing the path. So I like this geometrical interpretation very much because I find it like really surprising that it is so old. So for me, now the historical picture is complete. Okay, we need the contributions from Fresnel and Arago, the contributions from Pancharatnam, and the contribution, the rediscovery by Barriel of the work of Pancharatnam. And well, regarding this last topic, that is the Fresnel-Arago fifth law of interference, I brought like recently a historical manuscript, a paper making a historical review of this fifth law, because it's something that the fifth law of interference had been disregarded from other work, and I was highlighting here that for me it is the first description, and also it's a clear description of the geometric phase, especially not only by the original work by Fresnel, also by the second work from Fresnel from 1821 that I was commenting. Okay, I hope this is not too boring. I am almost reaching the end, but this is the last point I will comment. It's more research related. So Okay, geometric phases are something very common in nowadays research. A lot of publications in optics manuscripts. So let's see the small amount of work I have done when trying to characterize geometric phase optical components. And most of the components that you can find that are commercial are based on a half-wave retarder. So for this part of the presentation, I will consider which is the Jones matrix of a half-wave retarder. So basically, this is a general retarder. Okay, we make the retardance pi to have half-wave retardance, and we get this answer. Usually, this is presented as this, okay, with 1 and -1. If we rotate the retarder to a random angle, we get this answer, okay? We rotate this to an angle phi. Let's see what happens when this matrix is projected to a Stokes vector of circular polarization. So this is the Stokes vector of circular polarization. This is the Jones matrix that we have calculated. And when we do this calculation, again, there is one term that is multiplying both components, so it can go out. And curiously, this term is depending on the angle of the half-wave retarder. So this phase that I can anticipate we can call this a geometric phase, depends on the orientation angle of the half-wave compensator. In fact, my interest in geometric phases started because I bought some commercial geometric phase optical components, and they are all based on this effect. They are all based in making this angle, this orientation angle for the half-wave retarder to change in the space from point to point. Okay, so if we can make that this orientation angle is different at different points, we can achieve different phases for different points, which is the basic way to reshape a waveform. For example, a lens works by basically introducing a slightly different phase at different parts of a waveform. And for example, by doing that, you can achieve a focusing effect. Okay, so here, this can be done by polarization. Okay, by not only by polarization, by physical angles. Okay, in polarizing optical elements. So first, before going further, let's see why this is a geometrical phase. So let's go to the geometric representation. So first, let's consider a half-wave plate that is acting, that is a half-wave plate that is oriented at 45 degrees and that is acting on a beam having left circular polarization. So the initial state is here, left circular, and we use a half-wave plate oriented at 45, so the axis of rotation will be this axis here, and we apply a rotation of 180 degrees. We go from the south pole to the north pole, following this red trajectory, and we go to this state here, okay, to right-handed circularly polarization state. Now, let's consider a different trajectory on the space, on the Poincaré sphere, that is now given by a half-wave plate also, that is oriented not exactly like the first one, but oriented slightly different. So let's say that is 45 degrees plus alpha. Okay, so now the rotation angle, instead of being, sorry, this should not be alpha, it should be phi. Sorry, here it says alpha, it should be phi. Instead of being the axis of rotation instead of being this, the axis of rotation will be this. Okay, so we will go from this point to this point following this trajectory over here. Okay, if we do this, we go back to the initial polarization state. So what was left, it was right, and then it was left again. If we made these two beams interfere, we would see that after this round trip, the polarization states are out of phase, are not in the same phase. And the phase difference is this geometric phase here, okay? That in this case will be 2 times phi. Okay, similar, it's the same kind of plot that I have illustrated already before, but now with a different optical element, okay? Only as a side note, what happens if we do the same calculation with a Stokes-Muller formalism? We take the half-wave plate of the Muller matrix of a half-wave plate, we rotate it at a certain angle, and we project circularly polarization states to this half-wave plate, to this rotated half-wave plate. We see that we flip the polarization. Okay, we change from left to right, but we see no phase. Okay, this is only a remark. This is the only time on this presentation that I am using the Muller matrix formalism. It's only to show that it's not really useful to keep track of geometric phases. So here we don't have any phase. Okay, so what is the technological relevance of doing that with geometric phases? The technological relevance is that we can imitate the effect of other optical elements, for example, lenses or gratings, by just playing with orientations. And this is relevant because lenses work by changing the phase using thickness differences. So basically, light, this part of the waveform that goes through this part of the lens, travels a different a long distance through the lens. So the phase here of the lens of the wave will be different than the phase here. So it's thickness related. The phase, the change in phase is thickness related. The same for a grating. In a grating, for example, if we have a binary grating like this, we have two different values of the phase here and here that are related to the propagation distance of the light in the material. So it's thickness dependent. The advantage of geometric phases, at least for these elements, is that are not thickness dependent, that are orientation dependent. Okay, this is the advantage. So, a geometric phase optical element, in theory, can be very flat, can be almost zero thickness, almost. Okay, because it's not related. This phase is related to an orientation. Okay, it's not related to a thickness. So the commercial geometric phase optical elements that you can buy, at least to my knowledge, are lenses and gratings. Okay, and the thing is that these optical elements, when you shine unpolarized light to the lens or to the grating, you get always two contributions, because unpolarized light can be, for example, decomposed into left and right circular polarizations. So almost one half of light will follow the effect of the plus sign, and the other half of light will follow the effect of the minus sign, to put it somehow. And also there will be a small fraction of light that will pass through the material that will not really interact, so it will not diffract, and it will later discuss a little bit more about this part. But the technological relevance is this, is that they can be flat. The disadvantage maybe is that we have these contributions. Okay, we have both contributions at the same time, the plus and the minus contribution, at least if we use linearly polarized light, unpolarized light. So if we play a little bit more with mathematics, we saw that the Muller matrix, the Jones matrix of a rotated half-wave retarder was this one. If you do some algebra, you can see that this matrix can be decomposed in these two terms. Okay, this is an equal. So doing this, okay, we see that this is the Muller matrix of a circular polarizer, and this is the Jones matrix, sorry, of a circular polarizer of opposite handedness. So by doing this, and each one of them is going to have a different geometric phase. Okay, this geometric phase is different from here. So when we do this, okay, when we, for example, if we send light linearly polarized to this rotated retarder, we will get always a beam splitting. Okay, the phase profiles will split light into the left and right circular components, each one of them with a different geometrical phase. Okay, that's why commercial geometrical phases based on half-wave plate retarders always have special effects on the circular components of light. So when you handle in hand, for example, this is a geometric phase lens, and you use this lens to see something, you always see two images. Okay, we see if this is a lens, you see one image that is corresponds to a positive geometric phase that would correspond to for example, right-handed circular polarization, and the other image corresponds to the negative geometric phase that is the opposite circular polarization. So in this case, one lens is converging, and for the other polarization is diverging. So the nice thing about these lenses, well, nice or not so nice, depends on the application, is that they resolve light into circular components. So remember the calcite crystal. The calcite crystal was resolving light into linear components. Okay, whatever light we send, it gets the linear components, horizontal and vertical here. But for the geometric phase element, it's something similar. For any polarization or unpolarization we illuminate the sample with, we get circular components. And this is a nice illustration of something that is sometimes theoretically shown in physics courses, that is light can be decomposed always into a circular basis. So any polarization can be presented as the sum of two circular components, on the linear combination, sorry, of two circular components. So this is what these elements are doing. A little bit more related to the research I did with this commercial geometric phase optical elements. I was intrigued a little bit by the leakage wave. So the effect of the leakage wave only becomes evident if you consider that the retardance is not exactly a half wave, but is half wave plus a small difference. I mean, it's not ideally pi, the retardance. If you do this transformation, you see that the final result is can be splitted into two terms. One with the identity matrix, okay, and one that looks closer to what we had previously. If we rotate the result, we get one term that is basically the same as we had previously, and another term that is basically the identity matrix. And this term is going to vanish if this small perturbation from the half wave condition is vanished, is removed. So this term here is going to generate this leakage. Okay, and this leakage, the origin of this leakage is having a retardance that is not close to pi. But the interesting point is that even if there is leakage, even if it is leakage, the part that is not leaked, this part and this part, will have perfect circular polarizations. So this is interesting. So the non-ideality of the optical element will generate some leakage, but this circular polarization will be true circular polarization, and this will be true left-handed circular. So this non-ideality will only generate leakage, but will not affect the polarization quality of the leakage of the beams that have interacted with the structure. So in general, if you search for works reporting the effect of these geometric phase optical elements, you can find that basically these geometric phase optical elements will transform any incoming light into three terms: one plus, one minus, with circular polarizations, and one leakage term with that ideally should be not change the polarization of this leakage term. Okay. So in this work, we investigated a little bit with a Muller matrix polarimeter, which were the patterns, actually the orientations, the orientations of in a space of the of the azimuth of this half-wave retarder, how were these profiles. To justify a lens effect, for a lens, you need this kind of Gaussian profiles to generate a lens effect, but to generate a grating profile, you don't need this for a grating effect. It's enough with these linear profiles. Basically, from point to point, we are getting a half-wave retarder, but with different orientation. So the value of the retardance is more or less homogeneous everywhere. You can see that this element that does not depend on the angle theta is more or less flat, this element. Okay. So the value of the retardance is the same, but the orientation is different from point to point. Okay. Note that these commercial elements are quite non-ideal in the sense that the retardance is not really pi. If the retardance was really perfectly pi, this would be 0. It's not the case. It's not 0. It's not very far from pi, but it's not slightly pi. So that's the reason why these elements have some leakage. It's difficult to avoid. We measured also the phase profiles. Okay. From here, for example, you can deduce which is the focus of the lens. You can deduce the period of the grating, etc. if you calibrate. as far as I know, the company that makes most of these commercial elements is this Imagine Optics, and they use liquid crystal technology, polymerized liquid crystals to introduce this change on the azimuth of the half-wave retarder at different points of the space. And in fact, these are complicated structures because these structures tend to arrange vertically in a helicoid, and this generates also some optical activity that they compensate this optical activity by adding more layers with different twists. So it's sorry, it's not a simple very simple structure. But the thing is that this liquid crystal technology allows for a fabrication that is not very expensive. Okay, this is a curiosity to have higher diffraction orders in this. We don't get higher diffraction orders for this geometric phase grating because the phase profiles are sinusoidal. If the phase profiles were like binary, like here, we would get like higher diffraction orders. But these effects are quite dispersive, so it means that the different colors of light get different diffraction angles. Okay, this is just the almost last slide to point out that some people in some works are making like one step forward of this. Is not only controlling the angle, the geometric phase, the angle of a half-wave plate in this place, but controlling also the amount of retardation. Okay. So in each point in the space, they control both the angle and the amount of retardation, and then they can define like eigen states or states that are not linear and not circular, not linear like in a double refracting crystal, not circular like in a commercial geometric phase, but the eigenstates are elliptical. Okay, eigenstates. So it's like a generalization of both things, propagation phase and geometric phase. It's an interesting work. I don't know if it has a big application, but it's quite interesting, I think. Only a summary of this presentation is that we have started with a double refracting crystal. We saw that Fresnel and Arago were able to discover geometric phases basically only dealing with linear polarization states based on some geometrical interpretation that was close to the geometrical interpretation we can make in the equator of the Poincare sphere. And curiously, these geometrical phase effects that nowadays technologically ways are producing separations in the space of light and left circular components. That is like a complement of what double refracting crystals do for linear components. So for me, this is a beautiful round trip between different aspects. So crystals, double refracting crystals, geometric phases, and geometric phases and commercial geometrical phase optical elements. So I was happy to be able to understand all these things, because for me it's like a more or less complete picture now. So I can understand the historical perspective and the research that is made nowadays with geometrical phases. So I think my presentation was too long. I apologize. It's very, very long. So thank you for attending. I'm happy to answer questions.
Uh, Thank you, Professor Arteaga, for giving an overview of connecting how Fresnel-Arago fifth law to Pancharatnam Barifis and your specific work on Pancharatnam-based meta-surfaces. Now, we are open for questions. Maybe you need to unmute yourself and okay. Uh,
Hi, I have a small question.
Hi,
yes, sure.
hello.
Hello, Oriol. Your presentation was super nice. I'm like, it was so simple. I know even a first year student can easily understand, and like it was very nice. I have seen very less presentation like this, and like where you explain it in a very simple way.
Thank you.
So my question is on the last part of your presentation where you were
Yes,
telling the extent of meta surfaces. So where do
yes.
you see this polarization going into? I'm like, where is the extent of polarization in this meta surface? What these meta surfaces can do using polarization, like the far-fetched dream, if you could see.
Sorry, can you repeat a little? Can you repeat your question?
Oh,
Sorry.
sorry.
Yes.
What I asked is like, what do you see the extent of polarization in metasurface? What unachievable things can polarization do in metasurface? I'm like just
Yeah. Okay. Okay. I understand the perspective of this work. I am. I was thinking about that, and for I don't think I can clearly have an answer for that, because the I mean, for example, this work here, this is the most general work they they have been doing on meta surfaces and changing the retardation, and they were using it as a stocks detector. I mean, to detect like to combine this with a camera. Let's put it this way, to make an static detector of the Stokes vector, of the complete Stokes vector of light, based on these four states. It's an application that I don't think it's super relevant, because we have other ways of doing the same thing. So I I, I, I am a little bit skeptical. The application of this is, as it is now, the technology. I mean, as you can buy these optical elements, or you can fabricate. I am a little bit skeptical. They have a real big application that can surpass other techniques, standard optical elements. So the big advantage would be that they can be very thin, but
yeah. That's the only advantage, like thin and the very small. I'm like, if you have
thin
to,
and small, yes.
yeah,
But for me, it's not super clear, because the problem is that you in real life applications, in most cases, you don't want the polarization uh, different, because this these materials always have a different behavior depending on the polarization. So for polarimetric applications, this is good, having different response depending on the polarization. But for real world applications, when you mostly have unpolarized light, having two contributions is, I mean, beyond polarimetry, I don't. I mean, I am not good at finding applications either. So maybe there is a big application that I am missing,
thank you, thank you.
but they are very fun to play in the lab.
Hello, sir. I
Thank you,
have
Oriol. I
one
think it
question.
was a wonderful presentation in a way that uh, starting from the Fresnel-Arago interference and its connection to geometrical phase, and then through that geometrical arguments that Fresnel-Arago presented in terms of it understanding even without Poincare, it was really fascinating. And also then you talked about the metasurfaces, geometrical phase, optical elements through that, so which completes the circle. I think this is a wonderful presentation. I must thank you that the presentation with a wide forum to make it understandable. I think it was really a wonderful talk. Thank you, Oriol, for.
Thank you very much. Thank you very much, Nirmalia.
Hello, sir. I have one question.
Yes, yes, please.
In the Young's double slit experiment that you have in the 21 slide somewhere,
Yes,
uh,
yes,
so if you use in the one arm, if you remove one polarizer from the one arm, then what will
yes.
happen? Then what will happen? They will interfere or not?
Eh, if you remove one polarizer, they will mostly not interfere. I think not, but maybe you get. Mm, mm, mm. I would say they would not interfere, but I am having doubts if a portion of the light, that like some component of this light could interfere. It's a good question. I'm not sure I can give you an answer 100. Maybe Nirmalia or somebody else can give a better answer, but I'm not sure. I think you could see some small interference, like one intermediate interference,
So may I make
maybe.
a comment? Uh,
Yes, yes, sure.
yeah, I think there will be some interference, but the contrast will be depend on the state of polarization. So, suppose the
Yes, I
contrast,
think I agree. Yes.
so the contrast will change. So if you do not project them to the same polarization state, then the contrast will go down. So actually,
Mhm,
as Oriol was showing very beautifully, that how the degree of if through the Fresnel-Arago's laws of interference, that when you have start with unpolarized light and then you divide it into two orthogonal polarities and make them with a common polarization to interfere, they don't interfere. So this is basically you can think about the degree of polarization when we define. We say that EX star. So this
mhm,
EX star, so this has to equal to EX mod square or EY mod square that give you perfect contrast. So it is like interference of the orthogonal polarization. They are made to interfere in the same state. So therefore, degree
mhm.
of polarization will limit the contrast of the interference range. So in this case also,
Yes.
yes, yes. So I think that is
Yeah, yeah,
the
yeah. I fully agree. It will be like fringes, but with very
yeah,
low
low
visibility.
contrast. Yeah.
Yeah, thank
I
you,
think
sir.
it was very wonderful. We actually, all of us, we gone through that entire thing. It was very good that we understood that how basically, particularly this from Fresnel-Arago's laws, that and we say that the laws of interference of polarized light, and then it connecting it to the phase that Pancharatnam introduced, geometrical phase. It was a complete cycle, I must say. It was wonderful to listen to.
Yeah, it's
Oh,
very
thank you,
nice.
thank you. I mean, all this work on geometrical phases, it started because I bought these optical components in the lab, and I was not understanding them, how they work. So basically, that's why I started to look in Pancharatnam's publications, also in older publications from Fresnel. So all started with having these things in the lab and not really understanding how they work. So it's my approach was first experimental, and then I went to the theory.
Okay, thank you, Oriol. So, any other questions? Otherwise, maybe Athira, you can.
Yeah, so if there are no more questions, then we can call for the day. And once again, thank you, Professor Arteaga, for this wonderful talk. And hopefully, next time we can bring you to the
Yeah, actually,
campus.
we look forward to Oriol. We look forward to see you in our campus sometime soon.
Okay,
Maybe when
sometime.
things
I
will
hope.
become, yeah,
Yes,
when
yes.
things will
Meantime,
become
maybe
slightly
we meet
normal.
on some conference or some other activity.
Yeah, yeah. So particularly, we would like to have you in our campus at IISL Kolkata sometime very soon.
Yeah, maybe in the not very far future, traveling becomes easier.
Yeah, yeah, I think it
Uh,
will.
yes.
Thank you so much, Oriol. It was really wonderful for many of us to have an interaction, and we'll keep this interaction going, of course. That is
Okay, we
that is
keep in
important.
touch. Thank you
Yeah.
for attending, and sorry for the long presentation.
No,
Again,
it
thank
was
you for.
really good. We all
ag-
enjoyed. So we really enjoyed, starting from that Fresnel-Arago's interference laws to this Pancharatnam connection, etc. So this was really enjoyable. I mean, it was long, but it was very enjoyable. I think all of us enjoyed it.
I must
Okay.
add that many of the first year undergrad students were also attending, so it would have been beneficial for them as well, equally understandable to them as well. So
Because many of
Okay.
our attendees were not specialists in optics. So, just to give them a historical perspective on this Fresnel-Arago's laws of interference of polarized light, it was really good for
Okay.
all of us, I
Okay.
would say.
Okay. Okay. I feel better now. Thank you.
Thank you.
okay, thank you, Arteaga.
Okay, thank you.
Oh,
Thank you.
okay, then take care.
Bye. Bye.
Bye.
Thank you.
Thank you for
Bye.
everything. Bye.
Bye.
Bye bye.
Bye.
Bye. Bye, everyone.